Let's chat about the definite integral. We're going to start out looking at Riemann sums, which is an approximation of the signed area under the curve. If the curve is above the x-axis, we count that area as positive. We're trying for the whole area. And if it's below the curve, we count that as negative, okay? This is approximating the area from this dashed line A to this dashed line B and the signed area under the curve. Now, I borrowed these graphics from Desmos' site. Really cool. You can Google it, but that's the address also. This is called the left-hand Riemann sum, okay? And what we do is we approximate the signed area under the curve by approximating the height of each box at the left edge of that box. Can you see? I just approximated the height at the left edge of that box. And the width of the boxes is all even, okay? So how wide is each box? We'll call that width delta x. And it's just b minus a, the total width, divided by n boxes. I did 8 boxes. Can you see 1, 2, 3, 4, 5, 6, 7, 8. 8 boxes on all of these. But the cool thing about this Desmos page is you can move the endpoints A and B, you can move the number of boxes, and you can sort of see how it affects everything. So if you're going to approximate the areas of these boxes, what are you going to do? Well, you're going to sum, right? I'm going to use that sum notation. I equals 1 to 8, since I'm using 8 boxes here. In general, it might be sum I equals 1 to n, f ci. Well, what's ci? The ci is going to be in the ith interval. In this particular box, since I'm using left-hand Riemann sums here, right, this box I'm approximating this box at C1. So C1 is this x value. F of C1 is that height. It's negative. And then I'm going to multiply that times delta x. So f of C1 plus times delta x gives me the signed area of that box, which is negative. F of C2 delta x gives me the signed area of this box. Notice I'm taking the height again at the left edge. That's why it's called the left-hand Riemann sum of this box. This point would be C3 all the way over to wherever this box is, that's C8. Add those up, you have a left-hand approximation. These are all approximations of the same curve over the same interval. I've just changed where I'm approximating it. You can probably guess this is probably going to be an underestimate. See, I'm not counting that, I'm not counting that, I'm not counting that. And I have a little too much negative area too, so that's probably an underestimate. What happens for right-hand Riemann sum? Well, it's the same thing. We're calculating the area of each box. But here, C1 is going to be at the right hand of that box, C2. So again, delta x is going to be calculated the same way. We're going to add over n boxes. I'm going to take the height of each box, but now the only thing that's different is where I take the heights, okay? So that's what I have. That gets me a right-hand sum. So C8 would be at the very right-hand side of this last box. Notice that's probably an overestimate. Sound good? Well, maybe you say, well, maybe left's too low, right's too high, maybe this particular curve. You should take the middle of each box. Well, that would be fair to do. We can calculate where the middle of each box is. Delta x is going to be calculated the same way. Interestingly enough, the notation doesn't change at all, right? I'm going to add up the n boxes, f of ci, delta x. Well, that sort of leads to the definition of the definite integral. Okay, so what is meant by the definite integral? Well, let's see if we can't bring this up so you can have a look. Okay, so the definite integral over an interval a to b is the limit of the Riemann sums. So this integral is the limit as n goes to infinity. Okay, let's make these boxes. Maybe we could fix this and that. It turns out it doesn't really matter whether I'm using the left-hand sum, the right-hand, or the midpoint, as long as there get to be infinitely many boxes. The more boxes, the more accurate, okay? Of that sum, I equals 1 to n, f of ci, delta x, where, of course, delta x is going to be b minus a over that n, and ci is in the ith interval. Now, when that limit exists, we say that the function f is integrable over that interval. So we can actually figure out what the signed area is. Now, there are a number of properties that come immediately from thinking about what the definite integral is. What happens if you reverse the limits? So what happens if you had this picture going from a to b? You knew, oh, I know that's the integral from a to b. Notice the subtlety. I integrated from a to b here. What about from integrating from b to a? Well, if you think about this equation, what happens if b and a switch here? Really, you just have a negative in every delta x. And that follows exactly. If you start at the right and go to the left, the signed area is just going to be negative, the integral from a to b of f of x dx. It follows very technically from delta x, and it sort of follows intuitively. If you go right to left, it's positive, as long as it's above the curve. And if you go right to left, it's negative. What about adjacent intervals? Let's imagine you had this integral. Here's a, here's b, here's c, and we figure out sort of the signed area here. That's what this piece is. And this from b to c is the signed area there. Well, it really ought to work since you're going to infinitely many rectangles. You've got plenty of rectangles to go around. And the punchline is this really ought to be the same as the integral from a to c of f of x dx. Hopefully that sort of seems intuitive, but also you could technically sort of see that from that definition. Finally, let's imagine that the two functions f and g are integrable, okay? But f is less than g on the whole integral, on the whole interval from a to b. So here's a to b. Maybe f is even negative. There's f. G, oh, it's a lot bigger, right? So the signed area, this has some negative area and some positive area, but G has tons of positive area. What's obvious? The signed area under G had better be greater than the signed area under F.